Welcome to a new problem solving session. As usual, we have a problem at our screen. And what is the problem itself? What we got here is parallel rails of length 2L are fixed on a horizontal plane at a distance L from each other. There are two L's. Two identical batteries V with EMF E or Xi are connected to their ends. A jumper of mass M lies on the rails, this one, and can slide translationally along them. Okay, I think there should be no friction. The entire system is placed in a uniform vertical magnetic field with induction B. Assuming that the resistance of the jumper is equal to R and the resistance of a unit length of each of the rails is equal to rho. Resistance of unit length of each of the rails, that is resistance per unit length, is rho. Find the period of small oscillations that occur when the system is displaced from the equilibrium position. Neglecting attenuation, internal resistance of the sources, contact resistance, and inductance of the circuit. So I think our first job is to find out where the equilibrium position of the jumper is, where it can be. Since the batteries have the same EMF, and when the jumper is in the middle of the circuit, the both sides will have same resistance, and that means the potential difference between the centers of the rails will be zero, and that means if the jumper is at rest in the middle, then no current flows through it, which means that the ampere force does not act on it. Ampere force does not act on it in this condition. Therefore, this position is the equilibrium position of the jumper because I don't see any other force trying to move it. So, when the jumper is in the middle, that will be the equilibrium position of the jumper. And if the jumper starts moving from this equilibrium position, a current flows through it. This can be caused by a change in the resistance of the circuit parts, left and right, and also due to the phenomenon of electromagnetic induction. A wire moving in a magnetic field becomes a battery, and in accordance with the Lenz's law, part of the ampere force associated with the induction current leads to the damping of oscillation. I know this phenomenon often, and I also know that the part of the force is proportional to the speed of the jumper, and therefore is an analog of viscous friction, force of viscosity. So how can a simple harmonic motion is possible? But here comes the statement of the problem that says neglect attenuation. And when I tried to find what does it mean, I got that the EMF of the induction can be neglected when solving the problem. That means the EMF induced due to movement of this jumper that is bound to happen needs to be neglected when solving the problem. So to make things easier, I'm going to assume that let me draw a picture here. It is already drawn, so I just need to make it bigger. And here it is. This is the picture. And in this picture, X is very small. Suppose I just uh, gave a small push to the jumper from its equilibrium position. As you can see here, the push is towards the left, but it is very small. And if we put an origin here and the x-axis here, this x is negative. And what happens next? So I considered a small displacement of the jumper along the x-axis, and after the jumper moves along the rails by a distance x, current will begin to flow in it. That's right. And then I1, and let I1 denote the current flowing from left battery to the origin, and I2 denote the current branching from the origin to the jumper, as you can see here. That means it is the current flowing from the origin to the right battery, and the current no, I1 and I2, I misled you, sorry. Let I1 denote the current flowing from the left battery to the origin, and I2 denote the current branching from origin to the jumper. Okay. And I3 denote the current flowing from the origin to the right battery. Then we can write the Kirchhoff's first law here, and that tells you I1 equals I2 plus I3. Finally, we got our first equation. And we can also apply the Kirchhoff's second law. So let me write down the equation for this part of the circuit, and then starting from anywhere and just moving in a loop. In this loop, we can write if we move from here to here, we got a potential jump of xi, and then we move from here to here and we lose some potential difference, that is that in terms of IR, and that will be minus I1, because a minus sign because we are losing the potential. This length will be L minus X. If X is negative, we can write it L plus X as well, but X is, we have to remember that X is negative. Should I do this? Here, if you think X is negative, then we should write this length as L plus X. Write down this I1 rho L plus X. This is the resistance of this point. And then we move from here to here, and we lose another voltage, and this will be since we are losing, so I'm going to put down a minus sign here. I2 rho and the length is L. But its resistance is already given. Its resistance is different, capital R. So I don't need to write down these things. This will be minus I2R simply. And we reached again to this point, again to this point. So it will become 0. That means we have an equation like equation like I1 rho L plus X plus I2R equal to E xi, and that is our equation 2. And if you can see, if you can take the right loop of the circle, you can write an equation like this as but I'm missing something. There is this one also has resistance. That means this I should write it right here. Make it 2 times here, because this thing and this thing both will have the same resistance. So I should put it 2 here to make it. We moved it twice from we started from here, moved from here to here, and here again. So completed a circle, and from the right part we can start from here, and we can write an equation here like 2I3 rho L minus X. X is negative here. So I am writing here L minus X. Though if X is positive, we should write here L minus X and here as L plus X. And this will give you the same result, no problem. Minus I2R equal to E xi, and that is the equation number 3. And here you can do some manipulations and you can find I2. That is our plan, to find out I2. And I2 will be simply, if you find it, you will get it as xix divided by rho L square minus X square plus RL. If you want to neglect X by showing X is much less than L, because we have taken X very small, so X square is very much less than L square, and you can put here X square equal to 0 and simply write the result as minus Ex upon rho L square plus RL. This is basically your I2, considering all those things. And jumper is in a magnetic field and carrying a current, so magnetic force is going to act on it. And what will be that magnetic force? That magnetic force will be I2 LB. L and B are perpendicular to each other, so IL cross B becomes simply here I2 ILB. And put down the value of I2 and you will get everything LB along with it, and you will get minus ELBX divided by L rho L plus R. These are the things. And well, it is directed towards the right because X is already negative. So the magnetic force is positive. That means it is directed to the right. And the jumper tends to return return to the equilibrium position. And the equation of motion of the jumper we can write here is as mass into acceleration and equal to minus ELB upon L rho L plus R multiplied by X. And from here you can see, you can compare it with the equation A equals minus omega naught square X or omega square, whatever you like to write. I usually write the frequency of natural oscillation as omega naught and time period as t naught. So I'm writing here omega naught. You can put it omega here simply. And the oscillation of natural frequency of jumper, I get it as ELB upon ML rho L plus R. And always know that time period of oscillation is going to be 2 pi by omega naught, and you will have your result. Thank you very much for watching.